Okay, class, we're going to be doing lesson 3.4. These are measures of relative standing and box plots, okay? So I'm going to try to go through this as fast as I can because there's quite a bit of information, and hopefully you can slow it down and review it yourselves. First thing we want to talk about is a z-score. This is the number of standard deviations that a given value is above or below the mean. So you'll remember right here, this is our standard normal curve. Right here is the mean, the middle line, and you'll remember each of these represents one deviation away from that. And so when we find the z-score, it's going to tell us how many deviations we are away from the mean. 1, 2, or 3. Okay? And so that's what the z-score finds for us. Now the formula for z-score is, or for the z, our number that we're referring to minus the mean divided by our standard deviations. Now there's another, the formula is the same basically for the population, and so I'm not going to give that to us just because you can look that up yourselves. It's the same thing. Okay, in this case we're going to round the z-score to 2 decimal places because that's how it is on the charts. And we won't be using the charts today, but it'll become important to us in the near future. Now, remember when we were comparing the Chips Ahoy cookies with 30 chocolate chips, there were 40 cookies with a mean of 24 and a standard deviation of 26. And then we also were comparing the Coke that had a weight of 8.295. Its mean, there were 36 cans, it had a mean weight of 0.81682 and a standard deviation of 0.00751. Now, before we use the coefficient of variation, that's when we were talking about coefficient of variation, to compare variations of chips to weight. Now we can compare 2 individual data points using our z-score, okay? So let's take 30 chocolate chips, okay? So we want to find out the z-score for 30 chocolate chips. That's my x value. So that would be 30 minus the mean, which was 40, divided by the standard deviation, which in this case was 2.6. So we would solve that. In order to solve it, you guys need to do 30 minus 40 and then divide by 2.6, by the way. So make sure you do this first on top, then divide by 2.6. The answer will be 2.31. What that means is that this is 2.31 deviations away from, oh, I said 40. That was 40 cookies. The mean was 24. That's why your numbers wouldn't add up if you just did that. There were 40 cookies. The mean was 24. So it was the amount of 30, the mean of 24, and standard deviations of 2.6. What this means is this is 2, so 1 deviation, 2 deviations, 0.3 deviations, 2.3 deviations away from the mean. Now comparing that to the Coke, we have a weight of 0.8295, so that's our x, 0.8295, minus the mean, I won't mess up this mean, it was 0.81682 divided by the standard deviations, which was 0.00751. Now if you look back in the videos, this is one of the last things that we taught, so this should be fairly fresh to you, okay? When you solve that, again, you'll solve the top first and then you'll solve the bottom, and the answer you'll get is 1.69. That means this is only 1 and a little over halfway through almost the 2 deviations. So 1 and halfway through to 2, and that's where that would be. It's obvious though that this weight right here is closer in value in deviations to the mean than 30 is, and so we know that it's going to be closer to its own weighted mean. Alright, now ignore all these numbers down at the bottom. This is for something I'm going to do here in a minute. I'm purely focused on what's going on up here, okay? This is 1.69 deviations away from the mean. Okay, now an unusual value these have a z-score of less than -2 or more than +2. Okay, and that's the reason is because the majority of the information lies within 2 deviations. You'll remember that thumb rule that we talked about? Like 90 whatever percent is within 2 deviations. Anything up beyond the 2 would be unusual. So that means it's going to be, if the z-score is between -2 and +2, then this is usual. And if it's beyond -2 or +2 deviations, then it's unusual. Okay? Alright, so another word for usual is ordinary values. Okay, so a pulse rate is 48 beats per minute. Assuming the mean is 67.3 beats per minute and a standard deviation of 10.3 beats per minute, find out whether or not this is usual or unusual. Okay, so I'm going to write this information up here. I'm going to get rid of this because we've already talked about it. So here's what we had, okay? We had 48 beats per minute for this pulse rate. So that's our x value, 48. Minus the average person, or the average mean beats per minute was 67.3. That's the average or the mean. Divided by the standard deviations, that was 10.3 beats per minute. So each deviation is 10.3, so this would be 20.6, right? 2 deviations over. So when we solve that, we subtract the top and divide by 10.3 and we get -1.87. What that means is this is not quite 2 deviations down from the mean. So 1 and not quite 2, it lies somewhere in here. Since that is somewhere in between -2 and +2 deviations, this is a usual value, okay? And it's not unusual, so it's usual. All right, next, percentiles. Percentiles are the measure of location. Now, percentiles are denoted by P with a subscript of 1 to 100, basically, okay? Because percentiles are out of 100%. So these are measurements of location which divide the data into 100 groups with about 1% of value in each group. So if we were talking about the 50th percentile, which would be denoted by P subscript 50, that's the 50th percentile, that's how we denote it, then what we're basically saying is all the information, just about all the information, lies 50% to the left of that number and 50% to the right of that number. In other words, P of 50 is also the median. Okay, and we're going to be using the median value and P50 quite a bit here, so it's important to know that it's basically the median. Now, finding percentiles. When we're finding percentiles, we're going to round to the nearest whole. We have to do that pretty much, so just be prepared for that. Now, here's the formula for finding a percentile. The percentile of x, which is any number within the data, is equal to the number of values. I use pound to represent number of values, less than x over the total number of values and I'm going to multiply that answer by 100. Okay? And so that's how we're going to find a percentile of x. Now, here's where all these numbers down here at the bottom of this board are going to come into play, okay? These are the number of chocolate chips counted. We're stuck on this chocolate chip idea. I guess it's an easy analogy. So we want to find the percentile of 23. I'm just going to write it P23 like that. What we're going to do here, sorry, that would mean something different. The percentile of 23, where 23 is the x value, okay? So what we're going to do is we're going to find out how many values are less than 23 within that data set, okay? So let's go ahead and count that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values are less than 23. So the number of values less than x is 10. The total number of values, now I've already counted these all up, so there are 40. That's the total number of values times 100. When I divide 10 by 100, 10 by 40, when I divide that, I get 0.25. When I multiply 0.25 by 100, that basically tells me to move the decimal twice to the right, and I get 25, which is the 25th percentile, okay? So that means 23 is the 25th percentile. Okay. Now, some notations that we need to know, and I'm going to try and keep this data up here because I think I need to use it here again in a few minutes. This is going slower than I want to go. It's a little difficult to remember everything I need to tell you guys, and so that's why you guys sometimes see me making some mistakes. I never make mistakes other than that. Just kidding. Alright, so here's some notations. We have n. This is the total number of values in the data. We have k. This is the percentile being used. So in other words, P25, that'd be the percentile, which is the 25th percentile. Capital L, this is the location. The location of a value. So the 12th value means that L is going to be 12. Okay, the 12th value, 12 over, that's the 12th value. P with a little k, this would be the percentile. That's here, P25, that's the percentile, 25th percentile, or 50th percentile, P50, or whatever it might be, okay? So that's just a little bit for us to understand that. Now, let's say we want to find what number represents the 18th percentile. So what we're going to do here, that's P18. Alright? There's a formula for helping us find percentile. That is the number of numbers over, or the location, is equal to k divided by 100 times n, n being the total number of numbers in the data. So basically when we plug this in, that's going to be 18 over 100 times the total number of data points in the value, which is 40. When you solve that, you'll divide 18 by 100, then you'll multiply by 40. Just so you guys know, this is 0.18 times 40. Basically, it's taking this answer and making a decimal answer, moving the decimal twice to the left, 0.18. 0.18 times 40 is 7.2. Now, normally when we round this, we'll just say that the answer is 7. But due to percentiles, if we do not get an exact number, we'll always round a number up. So it's the 8th number. So L equals 8. Now that doesn't tell me the value, that just tells me I'm going to the position number 8. 1, 2, 3, 4, 5, 6, 7, 8. That position is 22. 22 is the 18th percentile. Okay? So I could write P of 18 equals 22, and that would be my answer. Alright, so you guys, I want you to find P25 here. P25. Stop, pause the video, and do that. Okay, what you should have done is placed 25 over 100, or changed it to 0.25, and multiplied it by 40, and the answer you would have gotten is 10. Now, here's one thing I didn't mention to you that you should know. If you ever get an exact whole number, like 10, then the answer is going to lie somewhere between the 10th and 11th term. So basically, we're going to count up to the 10th term. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 22. And the next term is the 11th term, 23. Halfway between those is 22.5. Now, if you don't know how to solve that, add those together, 22 plus 23, and divide it by 2, and you'll get 22.5. So anyway, 22.5 is the 25th percentile. Okay? It's pretty easy. So anytime you get a whole number answer, then the percentile will be between the 11th value and the next value up. Okay? Alright, quartiles. This is a measure of location. Now quartiles are represented by Q's. So we have usually quartile 1, quartile 2, and quartile 3. Those are the main quartiles that we deal with. 3 quartiles. Now these divide data into 4 groups of about 25% in each group, okay? Q1, I should have written these to the side, so I'll do that now. Q1, since these all represent 25%, that would be the 25th percentile. Or P25, I should just rewrite this. And then quartile 2, that would be P50. Now you'll remember P50 is the median. And then quartile 3, that would be P of 75, or the 75th percentile, okay? So that's important for us to also know that we're looking for those percentiles when we are looking for each of those quartiles. So let's say that within the data I was just referring to, we want to find quartile 1. Well, quartile 1 is the 25th percentile, right? So that would be 25 over 100, or 0.25, times the total amount of data here, which in this case is 40. And when we solve that, we would get 10, which we already know. 10, since it's a whole number 10, that means the 10th and 11th terms, halfway between them, that was 22.5. So 22.5 is the quartile 1. Okay? Now, let's say we want to go on and we want to find the quartile 2 and quartile 3s. I'm going to do that in just a minute. Let me talk to you about interquartile range. Interquartile range is the range between quartile 1 and quartile 3. So interquartile, IQR for short, is going to equal quartile 3 minus quartile 1's values. Quartile 1 being 22.5, quartile 3 we're going to have to solve here in just a minute. So let's go ahead and just finish out finding these quartiles so that we can build a box and whisker plot, which is one of the reasons why we might use this data. It helps, box and whiskers help us identify where the majority of the data is at. And so I'm going to erase what we have here because you guys have it already. Other than quartile 1, I'm just going to put what quartile 1 is. Now, Quartile 1 was 22.5, so that's taken care of now. Quartile 2, you'll remember, is the median. Now the median is the middle number. I've already taken the time to arrange the data from least to greatest. So what I would do here is I would start eliminating for both sides until I meet in the middle somewhere. Now it just so happens that the answer is 24. You guys can spend the time doing that. You can cancel them out one at a time until you get to the middle, which is something that I often do. Or you can just take the time to point and hope you don't mess up. Whatever it takes for you to, you first need to order it from least to greatest like I did, and then you need to find the middle number, which in this case is 24, I believe. Yep, 24. So 24 is the middle number. If you get two middle numbers, remember you add them together and divide by 2, and that gives you your median. Okay? Now quartile 3 is 75, the 75th percentile. The 75th percentile would be 75 over 100, which is really 0.75, times 40. When you solve that, you get 30. Now, remember that that means that we need the 30th term and the 31st term because it's a whole number. So the 30th term, I'm going to just count backward here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The 30th term is 26. The 31st term is 26. If you add those together and divide by 2, you're going to get 26. So that would be 26. Now let me show you what we do with this information to do a box and whisker. A box and whisker plot, I'm going to draw a number line that represents all the data within this sequence. This goes from 19 to 30. So I'm probably going to go by 2s. You can choose a scale that works for you. Hopefully you can see this on the screen. I'm going to start at, let's just say, 16. My next one over will be 18, 20, 22, hopefully this fits on here, 24, 26, 28, and we'll have 30 at the very end. Okay? Now, I should have written 30. It's my fault for not saving enough room. So what I'm going to do is this. I'm going to put a mark above quartile 1, which is 22.5. 22.5 would be right around there. Okay? I'm going to put another mark at quartile 2, which is 24, right there. I'm going to put another mark at quartile 3, which is 26, right there. And I'm going to draw a box around the middle point. And then what you do is just put a line through the middle point. That line represents that is the median value, okay? So there's the box. The majority of the data fits within that range right there, that inner quartile. The whisker parts is just putting a point at the least amount, 19. So 19 would be somewhere around here. And at the highest amount, which is 30. So 19, 30. Put a point at 30, which is at the very end there. And I just draw whiskers out to the highest and lowest point. That is a box and whisker plot. Helps you see where the range of all the data is at and where the majority of the data is within that box. Okay? Box and whiskers. They also talk about the 5 points. The 5 points would be the lowest point here, 19, the first quartile, second and third quartiles, and then the largest number, those would be the 5 key points, okay? So that they're talking about in the book. Now guys, it's important that we're able to identify an outlier. So it's hard, there's no, like, until now I just told you that an outlier was information too big or too small to really represent the majority of the data, right? Well, that doesn't help us out too much as far as being able to know exactly when we have an outlier. So an outlier is determined if the number, we are going to be able to determine whether or not something is an outlier. First thing we're going to do is we're going to find the inner quartile. And then we're going to multiply the inner quartile by 1.5. Now, if the number that we're looking at is greater than the third quartile by the answer of the inner quartile times 1.5, then we know we have an outlier. And if it is lower than quartile 1, by that same amount, then it is also an outlier. And I'm going to show you what that means here in just a minute. Now, a modified box and whisker, we're going to do a modified, and I'll show you, this will give me a chance to show you an outlier and a modified box and whisker, but basically an asterisk is used to identify outliers, and then the horizontal line and the box and whiskers, it starts with the lowest point that is not an outlier and the highest point that is not an outlier. Everything else is still the same. So let me give you some data so we can start this from the start, okay? So I'm going to erase this. We're going to try to do this the best we can, and as fast as I can, I'm going to write these down. I'm already arranging these in order from least to greatest because I know I have to do a median. So when you guys get these numbers, they won't be ordered from least to greatest. You'll have to do that. So here we go. 11, 12, 12, 12. Now you guys should already be able to tell me what the mean, median, and mode are with this, right? Because we just had that lesson. But anyway, if any number up here is an outlier, the numbers would probably be 21 or 11, right? If any of them are outliers. So we're going to have to identify whether or not they are an outlier. First things first, let's find quartile 1. Quartile 1 is 25% of these numbers. There are 24 numbers up there. So let's make sure I have them all. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23, 24. Okay, good. So there are 24 numbers up there. We want to find quartile 1. And that is 0.25 times 24, which is 6. Now guys, that's not the answer. Remember, that's the 6th number. So 1, 2, 3, 4, 5, 6th number. Since it's a whole number, we're in between the 6th number and the 7th number. If you add those two together and divide by 2, you're going to get 13. So there's my quartile 1. Quartile 2, again, it breaks it down to where I start on each side and I slowly make my way to the center points. In this case, my center point is 14, so that is 14. It's already in order, you can test it out yourself. Quartile 3 is 0.75 times 24. Remember, 24 is the amount of numbers there are. 0.75 is 75% of the way, basically. And when you solve that, you get 2.5. Now remember, if we get a decimal answer, oh, excuse me, that is not 2.5. I looked at the wrong spot. That is 18. Okay, so since that is 18 and it's a whole number, we need to do the 18th term. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So in between the 18th and 19th term, that's 15 and 16. 15 plus 16 divided by 2 will be 15.5. So here are my quartiles. Quartile 1, 2, and 3, okay? Now that's great. What we need to do now is we need to identify whether or not a number is an outlier. So we're going to find the inner quartile range, the IQR. Remember, that's taking the lower quartile, 15.5, and subtracting from it the lower quartile, quartile 1, 13. When we do that, we get 2.5. Sorry. Yeah, 2.5. Okay. Now, that's the inner quartiles, 2.5. Now, we are going to take that 2.5 and multiply it by 1.5 to find out how far a number has to be away from the upper and lower quartiles. This is the lower quartile, this is the upper quartile, in order for us to identify whether or not it's an outlier. So, I'm going to come down here, 2.5 times 1.5 equals 3.75. So, if a number is bigger than 3.75 away from the third quartile, or smaller than 3.75 away from the lower quartile, Q1, then we know that it is an outlier. Okay, so the lower quartile is 13. So that would be 13 minus 3.75, and that tells me that we are at 9.25. Is 11 smaller than 9.25? No, so 11 is not an outlier. Over here, 15.5, we're going to add the 3.75, and that gives me 19.25. Is 17 bigger than that? No. Is 21 bigger than that? Yes. So 21 is an outlier, okay? So in a modified, normally we would use 21 in the box and whisker, but because it's an outlier, we're no longer going to use it in a modified version. Okay, so that's if they want you to do a modified version. If it's not modified, you use 21, you're not going to be concerned with the outlier. But 21 is an outlier. It's too big for the rest of the information. Remember, I found the quartiles. I subtracted the upper quartile 3 minus the lower quartile 1, and I got 2.5. I took 2.5 and I multiplied it by 1.5. You will always multiply by 1.5, and I got 3.75. Then I took quartile 1 and subtracted 3.75 from it to get 9.25. All the numbers to the left fit within 9.25. They're all bigger than 9.25. And then I took the 15.5 and I added the 3.75 and I got 19.25. All the numbers are smaller than 19.25 except for 21. So 21 is an outlier. Okay, so here's how our box and whisker goes now. I'm going to erase all this data. It's no longer going to be useful to us. I mean, you have it written down in your notes or whatever you're doing to keep track of this stuff, and you can pause the video, do whatever you need to do, but 21 is an outlier. So when I do this, I'm going to just start with 11, 12, 13, 14, 15, 16, 17, and that's as far as we need to go. In that data, 11 was the smallest number that fit within it, so that's my whisker. 13 was the lower quartile. The median was at 14. The upper quartile was at 15.5. Draw my box around it, put a line through that. Here's my first whisker. Normally I would go to 21 here, but because this is modified, I drop off the outlier, and 17 is my next biggest number. So there's my modified box and whisker. Okay? Hopefully that made sense to you. If not, feel free to ask me questions and I'll do my best to help you understand this better.